We're now going to look at another way of being able to implement the big fraction reduction and multiplication application using a slightly different technique based on other ways of programming the Java fork join framework. And this particular method is called applyAllSplitIndex, and you'll see why we call it that in a second. This method, like the applyAllSplit method we just looked at, uses recursive decomposition to disperse tasks to worker threads. But it does it in a more clever way to reduce the overhead of some things, in particular copying of data. So the API is the same as before. applyAllSplitIndex takes a list, an op, and a fork join pool. But then the implementation is wildly different. And in fact, it's crazily wildly different. So the first thing we have here is we're going to use Java reflection in order to create a local array of type T. So we want to have a local array called results. And you'll see why we make it an array as opposed to, say, a list or an array list. So we make ourselves an array of this stuff. And to do that, this is a really bizarre quirk of Java and its generic programming model. You have to use reflection for a bunch of really strange reasons. And what we're doing here is we're saying, make me a new array that's going to have the type of the first element in the array, and it's going to be the size of the list. So now we have an array that we're going to use to store the results, an array of T. And yes, it's very ugly, and you can read more about why this particular technique is necessary if you read this link down below. So now we're going to have ourselves another nested class. This one's called splitter task also, but it's implemented quite differently from the one we saw before. The one we saw before extended recursive task. This implementation is going to extend recursive action. And you'll see why it's going to do that, because it's not going to return any values. It's going to use the results array instead. What we do now is we go ahead and we invoke this splitter task, and this splitter task is going to be given an index range covering all the initial contents in the array from 0 to size, which of course size -1, that's the last element. So we're going to say, start out with a new task that covers the entire array. And what we're doing here is we're using indices instead of copying data. And you'll see how this works when we look at the implementation. And then the final thing we do is we take the results list, the results array that comes back here. So we have a results array that's going to be modified by what happens here. We convert that to a list, and then we return that as the results of applyAllSplitIndex. And we need to do that because we're trying to be consistent with the types that are returned here. So there's a conversion that's going from list to array, and then back to list again. And that's incurring some overhead. So we'll see the good and bad about that in a minute. So here is another way of doing this. This is a more efficient way of doing this and less ugly way of doing things. If we're willing to change the signature of this method to this, then we can get rid of having to have this crazy reflection technique for making a local array. And we also don't have to convert things when we're done. So you can see here, because the results are passed in as a parameter, and then this implementation will put the results into the results, and then we just go ahead and basically return the result of doing all this stuff. So this turns out to be a more efficient way of doing things, since there's no conversion overhead. Here's what things look like in this implementation. It's actually quite clever. As you can see here, what we're doing is we are recursively partitioning the list and running each half in a fork join task, except this time it's going to be a recursive action, not a recursive task. And what we're doing is we're passing in indices to avoid having to copy sublists. So by using this index-based approach, we don't have to make copies of each half of the list. Here's what it looks like. It's even more complicated than what we did before, but it's still reasonable once you understand what's going on. So we figure out the midpoint, and then if the midpoint is one element, then there's just one thing to do. We go ahead and we take the list, get that element, we go ahead and apply the function to it, and we store it at that location in the results array. The results array is up here somewhere, defined as a local variable. So we're storing it into the array. Otherwise, what we do is we split the task, and this is clever. We make a new splitter task, which is going to be from low to mid, and we fork that. And then we call compute, and then we call join. And notice that we're not getting any return values here. We don't have to deal with return values. That's because we're using a recursive action, which doesn't require a return value. And the other thing to note is that we're doing these into the results array, so we don't have to copy anything. So we're using recursive decomposition to disperse tasks to worker threads, but we're not having to do any data copying. So by calling compute here, that computes the right-hand side in parallel with the left-hand side that's been forked, and then we go ahead and join the results together. And join is what's called a synchronization point, so it makes sure that the visibility is handled properly. If you want to read more about that, take a look at this link. There's no need to merge the left and the right items since they're already stored in the results array. So that reduced a ton of copying overhead. Now, this implementation is also harder to program and also harder to understand since it's recursive, and it uses this very clever technique with the array that we put the results into. Let's visualize this. This actually is pretty much identical visually to what we had seen before when we were doing the visualization of the applyAllSplit method. The only difference is it's just having a splitter task that works with indices as opposed to sublists. And as before, the subtasks are recursively decomposed onto worker threads in the pool, which means that we have very low work stealing overhead. We have very low copying overhead. There's still method call overhead because we're doing all these recursive function calls, but those are optimized pretty nicely for the most part nowadays, so that's not a big cost. And the forked subtask and compute subtask can run in parallel. And as before, we get a balanced tree of join calls, which is better than the iterative approach we looked at for our very first applyAllIter implementation. So that's the end of this model. You can see it's very similar to the one before, the applyAllSplit method. It just uses indices as opposed to copying sublists.